Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a video series on the product and quotient rules for Calculus 1. And we are at the very end of that series. Now we're just talking about synthesis problems. So these are problems that require you to kind of pull together a lot of information. They tend to not be the basic problems that you see initially when you're working through learning new topics. They're the kind of pet topics and also important topics because they showcase some really beautiful theory. And this very first example is one of my favorites in all of Calc 1. It's such a beautiful example. So let's go ahead and jump into it. You have a function, capital F. It's defined to be the product of two sub-functions, f and g, where f and g have derivatives of all orders. In other words, they have first, second, third, fourth, fifth, sixth, seventh, eighth, and thousandth derivatives, and so on and so forth. You could differentiate them forever. Show that f double prime is equal to this summation, and then do the same thing for the third and fourth derivatives, and then make a general statement about the nth derivative. So this is what I love about calculus, is that it's full of patterns, beautiful patterns, and all the patterns are just waiting for you to detect them. So f, capital F, is equal to little f times little g. Therefore, capital F prime is little f prime g plus little f g prime, just by definition, or actually not by definition, but by the product rule, which we proved early on. So therefore, if you take the second derivative, it will be, let's see, well, that'll be the second derivative of all of this stuff. Remember, we have let me write it this way. It's the next derivative of all of this stuff, I should say. It's not the second derivative, it's the next derivative in line of all of that. So we're going to take a derivative of f prime g plus f g prime. Now remember, we have a rule that says if you're going to take the derivative of a sum, you could split that apart into the sum of derivatives. That is, the derivative of f prime g plus, let me write that in green, it's supposed to be a plus fg prime, well, that can be broken into the derivative of f prime g plus the derivative of f g prime. Okay. Now, each of those subderivatives are products, right? So to take the derivative of this first group, whoops, wrong pen color. The derivative of that first group is going to be the derivative of the first thing, which if you take the derivative of f prime, it'll be f double prime, times the second, plus the first, times the derivative of the second. Again, that's the derivative of this group right here. The derivative of the first, so derivative of f prime being f double prime, times the second function, which is g, plus the first function, f prime, times the derivative of the second function, which will be g prime. Plus, now we take the derivative of that second group. Well, again, it's a product. The derivative of the first item is f prime, times the second item is g prime, plus the first item times the derivative of the second item. Well, that would be the derivative of the derivative, so it's g double prime. Collect like terms, and you see that you have an f double prime of g, or not of g, but f double prime times g, and you have two of these f prime g primes, and then finally an f g double prime. Well, that's kind of cool. Let's go ahead and take the third derivative of capital F. And again, you're just, now that you can see it, you have 3 objects you're taking derivatives of. And I don't need that 2 in there. So the objects I'm taking derivatives of are going to be f double prime g. I'll take a derivative of that. And an f prime g prime, I'll go ahead and take a derivative of that. And an f g double prime, I'll take a derivative of that. This will lead us to our 3rd derivative. So I'm just taking the derivative of the 2nd derivative. You might be wondering, wait, how did he just know to pull the 2 out? Well, if you have a factor that is a constant, we have a theorem that says that if you take the derivative with respect to x of c times a function, that's the same thing as c times the derivative with respect to x of the function. So you can factor out constants. All right. Here I go. The derivative in this first group, the derivative of the first item would be f triple prime times the second plus the first item, f double prime, times the derivative of the second. All right, that's not bad. Plus 2 times the derivative of the first item, f double prime then, g times the second item, plus the first item times the derivative of the second item. And finally, the last group, the derivative of the first item times the second item, plus the first item times the derivative of the second item, which would be a triple prime. And again, collect like terms. You have a triple derivative of f times g, plus I have one set of f double prime g primes there and 2 more of them right there. So I have 3 of them all together. F double prime g prime. And I have, let me get my highlighter ready, 2 of these f prime g double primes, plus another f prime g double prime. So altogether I have 3 of those. And finally, I have an f g triple prime. So let's see, do this for the 3rd and 4th. So we've done the 3rd, and now we're to the 4th. I want to just showcase something. Coefficient here was 1, 2, and a 1. The coefficient here was 1, 3, 3, and a 1. You should notice something with these numbers already. If you don't notice, then the 4th derivative should do it. Remember, when you do a 4th derivative, we stop with the prime notation. And this time, I'm just going to power through. So here we go, taking the derivative of this black ink up above. So we have the derivative of the first times the second plus the first times the derivative of the second plus 3 times the derivative of the first times the second plus the first times the derivative of the second plus 3 times the derivative of the first times the second plus the first times the derivative of the second. Finally, plus the derivative of the first times the second plus the first times the derivative of the second. Collecting like terms. It's the 4th derivative of lowercase f times g plus, let's see, triple primes on f. You have 1, 2, 3, 4 of them, so plus 4 f triple primes times g prime. Plus, as far as double primes on f, you have 3, 4, 5, 6 of them, I see. You can double check by just counting them up. Plus, as far as single primes on f, you have 3, 4 of them. They are attached to g triple primes. And finally, you have just 1 of those f g 4th primes. And that should convince you, finally, what these coefficients are. These are the numbers within Pascal's triangles, Pascal's triangle, also known as the binomial coefficients. So Pascal's triangle, if you don't know much about it, it's a beautiful triangle. You make it by taking diagonals, you start with 1, 1, 1, 1, and then you add those two together to become a 2, 1, and then let's see, 1, add these two becomes 3, add these two becomes 3, and then 1, and then let's see, 1, add these two together to get 4, add these two together to get 6, add these two together to get 4, and then 1, and you can keep going. These are the coefficients of binomial expansions. So a plus b to the 0th is 1, a plus b to the 1st is 1a plus 1b, a plus b to the 2nd is 1a squared plus 2ab plus 1b squared, a plus b to the 3rd is 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed, and so on and so forth. Right? This is from your pre-calculus course, but still very cool stuff. That pattern actually holds when you take higher derivatives of functions. Notice I didn't tell you these are polynomials. I just said these are functions. And so that's really neat. If you have a product, so if somebody says I've got a product of functions, I don't care what it is, and you want to take the 5th derivative, I wouldn't just start there and take 1st, 2nd, 3rd, 4th, and then 5th derivative. I would write out Pascal's triangle so I can find out their coefficients, and I would know, okay, it's the first function, the 5th derivative of it, times the 2nd function, and then decrease the derivative order on the first function while increasing the derivative order on the 2nd function. It's a really cool way to take derivatives of products, higher derivatives of products. Really cool problem. Let's see what else we have. Okay, so here we have a couple functions, f and g. F is in, I guess that's magenta, and g is in blue, maybe. Let u be the product of them, and v be the quotient of f and g. Find u prime of 1. Remember, u is their product, so u is f times g. So u prime would be f prime g plus f g prime, and u prime at 1 would be f prime at 1, g at 1, plus f at 1, g prime at 1. I consider this a synthesis problem because you're pulling together your algebra skills and your graphing skills and the derivative skills you've just learned. So let's see what f prime at 1 is. Now here's 1 right there, x equals 1. So you can compute the slope of that pretty quickly. The rise, it rises 2 units when it runs 1. So f prime at 1 is 2. G evaluated at 1 is 1, plus f evaluated at 1 is 2. And finally, g prime evaluated at 1, well, that's the slope of this line, and that is, it falls 1 when it runs 1, so it's a slope of -1. And so this ends up being 2 minus 2, or 0. Well, that's kind of nice. Now that we have that done, let's focus on v prime at 5. Well, v prime, well, maybe I should start with v. V was told to us to be f over g, which implies v prime is equal to f prime g minus f g prime all over g squared, which will imply that when we want to evaluate v prime at 5, we just need to plug 5 into all these values. F prime at 5, g at 5, minus f at 5, g prime at 5, all over g of 5 being squared. So this just, again, forces us to kind of look at the graph and figure out the slopes. For example, if this is 1, there's 2, 3, 4, and 5. So f prime at 5, the slope right here. Well, it seems to be, I'll just use this as a guide, it falls 1 when it runs 3. So that's a -1/3 as a slope. G evaluated at 5 is 2. F evaluated at 5 looks to be 1, 2, 3 maybe? And G prime evaluated at 5. Remember, that's just a slope of g evaluated at 5. I usually look for when it crosses another point. So these two are good ideas. It rises 2 when it runs 3. So 2/3 is the slope there. All over g at 5 squared. Remember, g at 5 is 2, so you square it, it's 4. And now you can simplify this out. I would multiply both numerator and denominator by 3 so that you get -2 minus 6 all over 12. And that's -8/12. Divide by 4, that's -2/3. Let me just double check my mathematics before I commit to this. -2, -6, 12. Yep, that's right. So again, I just picked on that as a synthesis problem because you're using your old school algebra skills and graphing skills for function evaluation here. So it's always nice to see problems like that mixed in. And finally, we get to what I consider to be probably the most challenging of the examples. How many tangent lines to this curve pass through the point 1, 2? So let's just focus on that sentence there. How many tangent lines to that curve pass through a point? That point might not even be on that curve. So really, if you want to visualize this, it might help out. So that curve, x over x plus 1, y equals, is a rational function with a horizontal asymptote at -1, and I'm sorry, vertical asymptote at -1, a horizontal asymptote at +1. When x is 0, it goes through 0. So there we go. And we don't have any other information about it. So I'm going to say that it probably looks like this. Like that. And also like this. Whoops. Like that. Okay. So this is kind of the graph of the curve. In fact, I'll go ahead and erase those just to get them out of the way so you can see it. And we're given the point 1, 2. Let's just pretend as though that point 1, 2 is like out here. Now, there probably are at least a couple tangent lines to this curve that go through that point. For example, maybe this tangent line and maybe a tangent line that strikes the curve way out there or something like that. So that's the visual of it. It's very, very difficult to visualize this without graphing, honestly. So that's why I'm just quickly scratching on a graph. All right, so now let's talk about the words here. Tangent line. All right, well, if I need a tangent line, I need the equation of a tangent line. And the equation of the tangent line is always y minus y1 is equal to slope times x minus x1. And the slope is actually the derivative of that curve at that point. Now let me say that again. I'm going to zoom in maybe to this right here. So the slope of the curve right there, should have used red, slope of the curve right there is just f prime at whatever that value is. I don't really care what the value is, but it also contains the point a comma f at a, right? So you have two pieces of information, the point and the slope. And so therefore the equation of the tangent line at that moment, if I just replace these x sub 1, y sub 1, just to keep my lettering consistent, if I said the x value was a and the y value is just f evaluated at a, then m, the slope, is just the derivative of our function evaluated at a. And then I can kind of leave it like that if I want to. So that's the equation of the tangent line. Now I just need to find out what is f prime in general. So here's our function. Let's go ahead and find out what its derivative is. Y prime is equal to, derivative of the top is 1 times x plus 1, minus the top times the derivative of the denominator is also 1, all over that denominator squared. And you can see this simplifies quite a bit to 1 over the quantity x plus 1 and quantity squared. Great. So let's go ahead and go back to our tangent line. Remember, our tangent line to our curve at any given moment is just a, whatever our value that we're at, and f of a goes right here. Well, we happen to know what f of a is, actually. F of a is just our given function evaluated had we just plugged a in. So I'm going to go to the function. It is a over a plus 1. In fact, I should probably write that in blue just to keep consistent, right? And this should equal the derivative evaluated at a. We just computed that, so that's 1 over a plus 1 and quantity squared times x minus a. We still don't know what a is, but there you have it. So far, I haven't really read too much into the problem other than I needed the equation of a line. So I started with that idea of, oh, equations of a lines are like this. And then I read even further and they said, oh, tangent line to this curve. Okay, so I have a point on that curve called a comma f of a. That's why I wrote those two down. And then if it's tangent to that curve, the slope is the derivative of that curve at a. Then I just found the derivative and I plugged all those values in. Now let's see what else they need me to do. How many tangent lines? Oh, I need this tangent line to pass through the point 1, 2. So I'm going to write that down. I need this line to pass 1, 2, or pass through 1, 2. That is, when the y value is 2, I want the x value to be 1. So we're going to solve 2, letting y equal 2, minus a over a plus 1 is equal to 1 over a plus 1 quantity squared times 1 minus a. We're basically just going through and seeing, like, can this happen? Is there a solution to this equation, essentially? Because if there's no solution to this equation, then there's no tangent line that will ever go through that point. That's a great way to think about it. If I can't find a solution here, then there's no way I can get a line to pass through that point. I'm going to multiply both sides by a plus 1 quantity squared. So this is 2 times a plus 1. And you can see why this is synthesis. This has a lot going on. This is equal to 1 minus a. And then just go ahead and actually, combine. You could multiply out, I suppose. Let's go ahead and do that. This is 2a squared plus 4a plus 2. Let me see, that's right. Plus a squared plus a equals 1 minus a. Collecting everything up, that's 3a squared. How many a's do we have? 4a, 5a, add another 6a. And 2 minus 1 is 1. All right. So we get down to this guy right here. Oops, and I see that I missed a sign here. This is supposed to be a minus. So these will change to minuses as well. My bad. Watch your arithmetic. So all this will change slightly. Let's see. I had a squared. Oh, 2a squared minus a squared. Oh, this is nicer. 4a. That's it. And then still I have a plus 1 here. It's equal to 0. Let's see if there's a solution to this equation. I'll start with the discriminant. Discriminant is b squared minus 4ac, which totally does, it's greater than 0, so therefore I know that there's going to be a solution, actually 2 solutions to this equation. So let's go ahead and find them using the quadratic formula. The opposite of b, plus or minus the square root of 12 over 2. And by the way, I pre-compute the discriminant because you're going to need it anyway, so why not? This is going to be a negative 2 plus or minus root 3 when you simplify it down. So they're totally 2 tangent lines, 2 values of a, or 2 x values, which give tangent lines striking the point 1, 2. Let me actually say that. There we go. Thus, there are 2 values of x. One is negative 2 plus root 3. One is negative 2 minus root 3, for which the tangents at the points a, f of a, and I just used that because I didn't want to write negative 2 plus root 3, f of negative 2 plus root 3, and so on and so forth. But those tangents go through the point 1, 2. Did they want me to do anything else here? Gosh, at which points do these tangents touch the curve? Shoot. Oh, well, that's okay. Which points do these tangents touch the curve? At negative 2 plus root 3, f of that? So these tangents occur at these 2 points. You could compute those 2 points. I'm just too lazy to right now because I've been recording all day and it's my birthday and I don't want to record anymore. So there you go. That is a good, very high-level synthesis problem I think a lot of students would struggle with, but it's good to kind of see that style of problem being worked out. So I highly recommend that you rewatch this video if you need to. Otherwise, you have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just